Welcome to the video on biasing for MOSFET. First, let us see what is biasing in MOS amplifier circuits. In the design of a MOSFET amplifier circuit, an essential step is the establishment of an appropriate DC operating point for the transistor. This is also known as biasing or bias design. The appropriate DC operating point or bias point is characterized by a stable and predictable DC drain current ID and by a DC drain to source voltage VDS that ensures the operation of the transistor in the saturation region for all expected input signal levels. Next, we are going to see about the types of biasing. There are actually 4 types of biasing in MOS amplifier circuits. The first is by fixing VGS, second one is by fixing VG and connecting a resistance in the source. Third one is using a drain to gate feedback resistor, and finally it is using a constant current source. So let us see one by one. The first one is biasing by fixing VGS. This is the most common approach of biasing a MOSFET. That is, we fix the gate to source voltage VGS to the value required to provide the desired ID. This voltage is derived from the power supply voltage VDD through the use of an appropriate voltage divider. We generally know the ID current, that is the drain current equation of a MOSFET, that is half mu n Cox W by L into VGS minus VT the whole square, where the threshold voltage V0, the gate oxide capacitance Cox and the transistor aspect ratio W by L vary widely among devices of same size and type. But this biasing technique is not a good approach in biasing of a MOS amplifier circuits. The graph here, which is ID and VGS characteristic curve representing the extreme values in a batch of MOSFETs of the same type. For the fixed value of VGS, the resultant spread in the values of the drain currents can be substantial. Next, we are moving on to biasing by fixing VG and connecting a resistance in the source. This is an excellent biasing technique for a discrete MOSFET circuits consisting of fixing the DC voltage at the gate, that is VG, and connecting a resistance in the source lead, that is RS, as shown in this figure. Now, applying KVL to this region, we get VG is equal to VGS plus ID into RS. If VG is very greater than VGS, then ID will be determined by the values of VG and RS. If VG is very greater than VGS, resistor RS provides negative feedback which will stabilize the value of the bias current ID. From the equation, when ID increases and VG is constant, then VGS will decrease, which will further decrease ID. Thus, the RS works to keep ID as constant as possible. So, this negative feedback action of RS gives it the name degeneration resistance. So, next we are moving on to the third type, biasing using a drain to gate feedback resistor. This is a simple and effective biasing arrangement utilizing a feedback resistor connected between the drain and the gate as shown in this figure. Here the large feedback resistance RG forces the DC voltage at the gate to be equal to that of the voltage at the drain. So thus we can write VGS is equal to VDS, which is equal to VDD minus ID into RD, which can be rewritten in the form VDD is equal to VGS plus ID into RD. If ID increases due to any reason, then VGS must decrease. The decrease in VGS in turn causes the decrease in ID. Thus, the negative feedback or the degeneration provided by the RG works to keep the value of ID as constant as possible. Finally, we are going to see biasing using a constant current source. See, can you see a constant current source which is attached to the source lead? The most effective scheme for biasing a MOSFET amplifier is this technique. Okay, so here the RG establishes a DC ground at the gate and presents a large resistance to an input signal source that can be capacitively coupled to the gate. Resistance RD establishes an appropriate DC voltage at the drain to allow for the required output signal swing while ensuring that the transistor always remains in the saturation region. So I hope by watching this video you'd have clearly understood about the 4 types of biasing in MOS amplified circuits. Thanks for watching.